All right, so here we are for section, what is this, 8.5. In section 8.5, we're going to take a look at probability distributions and expected values. So what we're going to do is we're going to attempt to try to tie together this idea of probability and how it ties into application, like what people use this stuff for, okay? All right, so we're going to take a look at some random variables, define what a random variable is. We'll take a look at a probability distribution. We'll calculate and define expected values. So first off, a random variable is a function that assigns a real number to each outcome of an experiment. So up till now, we've had experiments, and our experiments could have sample spaces, and sample spaces could be things like heads or tails if we had an experiment where we were flipping a coin. What we're going to do in this section is we're going to assign values by using a random variable to those outcomes. So we're going to assign numerical values. So maybe I'll say a head is a 1 and then a tail is a 0. So then my sample space is no longer heads and tails. My sample space is zeros and ones. And then when I flip the coin, I don't see heads and tails. I see zeros and ones. So basically what we need to do to make the math come out in this is we need to redefine how we look at the outcomes of an experiment so that everything is numerical. Here's what I mean by that. Our first example. Suppose that a local basketball team is holding a raffle where 2,000 tickets will be sold. All right, so we're selling 2,000 tickets. We're selling them for $156 a piece, but there are several prizes you can win. So you may win a $1,200 gas card. You could win a $500 airline voucher, or you could win a $100 gas card. Now I just realized something. This is a typo. This really shouldn't say $156. It's supposed to say $15. But evidently when I was typing this, I fat fingered that thing and typed in 156 when I should have typed in 15. Okay? What I would like to do is I would like to write out the sample space for this experiment using a random variable approach, right? So normally what we do is if we said, what was the sample, we say the sample space is, well, you could win the ski, or you could win the plane, or you could win the gas card. Right? But what I want to do now is I want to think of this as not a ski trip and a plane ticket and a gas card. I want to think of this as a numerical value, the worth in this case of each of these. So what is the value of the ski trip? Well, the ski trip is valued at $1,200, so its expected value would be $1,185. Now, if you're wondering where on earth that came from, well, if I paid $15 for the ticket and I win that prize, I really didn't win $1,200. I won the $1,200 minus the money I paid to play that game. In this case, $1,185. Okay. If I win the airline voucher, technically it's worth $500, so then the numerical value would be $485. Right. The third outcome is I could get a gas card, but those are really only worth $85 to me. And then I have to include a new outcome. And that new outcome is this. Because while there's only those three prizes in here, technically there's a fourth outcome in there. There's a fourth possibility in that sample space, and that is that we bought a ticket for nothing and we lose all of our money. So lose $15. And so this would be our sample space for our probability experiment by a raffle ticket using a random variable. There are four possible prizes. The four possible prizes are I could win $1,185, I could win $485, I could win just $85, or I could lose my money. Sample space, random variables. Okay. Now, a probability distribution is now going to be a table that will list all of those random variable values and their probabilities. So a probability distribution is going to look like this. It is going to be a table that is going to have a row for the x's and then a row for the probability of those x's. So it's going to have a row for the x's, 1,185, 485, 85, and negative 15. And then it's going to have a row below that where we're going to have to input all those probabilities. 1 out of 2,000. And where did I get that 1 out of 2,000 for the probability of the random variable value being 1,185? Well, remember, the 1,185 is the ski trip, right? There's one ski trip, one ticket out of 2,000, right? The 485, that's the plane ticket, right? There's one of those, right? One airline voucher, so that's also going to be 1 out of 2,000. The $85, though, that's the gas card, and I believe that there were 9 of those, right? And so that would be 9 out of 2,000 because there were 9 gas cards, right? And then the last one is I didn't win anything. I lost my money, right? I know it's going to be something out of 2,000, but what's that going to be? Well, if there are 9, 10, 11 winning tickets, that means there's 2,000 minus 11, or 1,989 losers. And now I have my probability distribution. Now, probability distribution, again, just to recap, is going to be a table that's going to have a row for the random variable values, and it's going to have a row for the associated probabilities. Now I'm saying row here, but even as I'm saying it, I'm wondering about it. I've never seen anyone do it, but I believe that you probably could do it vertically if you wanted, and have this then be the 1 out of 2,000, and so on and so forth, right? I've almost always seen them drawn sideways like this, but I can't think of a reason why you couldn't do it vertically. It just needs to be a table that lists all those possible values for the random variable, and the probability. All right. For each experiment below, let X represent the random variable and use your knowledge of probability to prepare a probability distribution. So we'll start with number 1 here. Problem number 1 reads, 4 coins are tossed and the number of heads is noted, and my job is to make a probability distribution. So for number 1, I'm going to have an X, I'm going to have a P of X, and I need to figure out probabilities. So 4 coins are tossed and the number of heads. Well, I could get 0 heads if I tossed it. I could get 1 head if I tossed it. I could get 2 heads if I tossed it. I could get 3 heads if I tossed them, or I could get all 4 heads if I tossed it. Now I need probabilities to put in here, because these probabilities right here need to be the probability for all those X's. Now I know if you're looking at this, you're probably noting that that is just binomial. So I'm going to go ahead and bring up my binomial calculator here, and I'm going to say, let's see, second distribution, binomial PDF. There were 4 coins that are being tossed. Probably a success is 0.5. And I want X to be 0. 0.625. 0.0625. And then I want to do that again, but I want to have 1 head. So that's going to be 0.25. Then I'll do it again, because I want it to have 2 heads, 0.375. And then I'll do it again because I want it to have 3 heads, 0.25. And then I'll do it again because I want it to have all 4 heads. And I get 0.0625. And there's my probability distribution. All right. Problem number 2. 2 dice are rolled and the total number of points is recorded. All right. So if 2 dice are rolled and the total number of points are recorded, x, p of x, if I roll 2 dice, the smallest sum could be a 2, or I could get a 3, or I could get a 4, or I could get a 5, 6, 7, 8, 9, 10, 11, or I could roll a 12. Now, I happen to know a little bit about rolling 2 dice. I know that there are 36 ways for the dice to possibly land, because if I think about what's going on here, there's a 1, 2, 3, 4, 5, 6 for the first die, 1, 2, 3, 4, 5, 6 for the second die, and then everything in here is going to be the sum of those 2 dice rolls. Okay? And it looks like there's one way to roll a 2 right there. And so if I think about this as intersections, every single one of those boxes is going to have a number. That's going to be a 3, that's going to be a 4, that's going to be a 5, 6, and a 7, and a 3, 4, 5, 6, 7, 8, and a 4, 5, 6, 7, 8, 9, and a 5, 6, 7, 8, 9, 10, and a 6, 7, 8, 9, 10, 11, and a 7, 8, 9, 10, 11, and a 12. And so when I look at what's happening here, I can read from this where everything, how everything, when everything is going to happen. I can find those probabilities. Well, there's one way to roll a 2 out of those 36 ways. That's that one. So I'm going to cross it off. There's 2 ways to roll a 3. So that's going to be 2 out of 36. There's 1, 2, 3 ways to roll a 4 out of 36. There's 1, 2, 3, 4 ways to roll a 5. There's 5 ways to roll a 6. There's 6 ways to roll a 7. 1, 2, 3, 4, 5, 6. And then it starts climbing back down. 5 out of 36. 4 out of 36, 3 out of 36, 2 out of 36, and then 1 out of 36. And there's my probability distribution. Oh, this isn't too bad. I just need to find out what could possibly happen, find all the probabilities, and call it a day. I'm picking cards now for this next one. 3 cards are drawn from the deck. The number of aces is counted. Well, I could pick 0 aces, 1 ace, 2 aces, or I could pick 3 aces. Right? Now I need to figure out what those probabilities are. Right? Well, the probability of 0 aces. Well, in the deck, there are 4 aces, and there are 48 cards that are not aces. And there's 52 cards total. So let's see, if I want none of the aces, that means this is going to be 48 pick 3 over 52 pick 3. And if I want 1 ace, that's going to be 4 aces pick 1 times 48 cards pick 2 out of 52 cards pick 3. And if I want 2 aces, that's going to be of the aces pick 2 times of the not aces pick 2 divided by 52 cards pick 3. Oops. I'm sorry, I misspoke right there. We're only picking 3 cards total. So pick 2 aces and then pick 1 not ace. And if I want them all to be aces, it's just 4 choose 3 over 52 choose 3. Now, I don't know what these numbers are, but I could punch all of this into my calculator and get numbers there, a numerical value, and then that will be my probability distribution. I believe that you can push those buttons out. So my job is to be able to make a probability distribution. A probability distribution is simply just a table that contains numerical values for all of my outcomes and the probability associated. So whether it's rolling dice, flipping coins, picking cards, I'm giving a numerical outcome to the experiment, and I'm finding probabilities. All right, I'm going to end this one here and come back. We'll do the second one, the expected value part.